Hello guys, welcome to this session. In this session, we're going to study improper integrals. So we're going to study improper integrals 7.8, the improper integral. Okay, so what did we learn so far, guys? So far, we actually learned, area under the curve, this type of things, right? And if I make a little sketch, so suppose I have a curve. Let me make this better. Suppose I have this type of curve, okay? So, and this guy, I call this guy A, this guy B, okay? Keep in mind, this is your x-axis, this is your y-axis, right? And then this curve is defined by y equals f of x, okay? Now, how do you find this area? Pretty much I'm concerned that the area under the curve is this shaded portion. So far we've learned this guy, right? We've discussed it. So now we're moving into situations where, so what about, okay, so we're moving into situations where we might have an asymptote, okay? Okay. What about situations where, let me give you an example. This case, guys, suppose this guy is, suppose I have a curve here, another curve here. This is my x, of course, this is my y. Okay. All right, so this guy, over here we have initial point A. We have a point here, we call this guy B. So the area under this curve, pretty much we're talking about these guys. Okay, so this is our focus. What if we have this, this type of geometry? What happens now? Or the case where this should be over here, this should be infinity. Okay, so what if I have a to infinity? So, or I got this situation. Okay, let me make a sketch for that guy too. So this is still my x-axis. Suppose we have a curve that glides down, doesn't really touch x, but it flats around x. Okay, this guy is still my y equals f of x, right? Suppose we have an initial point A. Over here, we have this guy. Sorry, this should still be an A. Going by the geometry I have, this should be from A to B, actually, because I have the endpoint, initial point A and the endpoint B. So going from A to B. But in this case, you have just a starting point. You don't have an ending point. So that means you're going from A to infinity. So now these are three different cases, right? So suppose this guy is what we call, suppose I call this guy case 1, case 2, and case 3. Now with respect to case 1, we've studied things like this before. There's no problem about that. What if I have a situation with case 2? What do I do? What if I have a situation with case 3? What do I do? So, and that's what we actually want to study. Now, let me make a definition, guys. Okay. Definition. Now we want to actually define an improper integral. Improper integral. Okay, so let me make this definition by saying that, letting you guys know that an integral with an infinite interval. Okay, say, let me give you an example. That is a to infinity, from negative infinity to b, and then from negative infinity to infinity. Or we can say, or an integral where the integrand has an infinite discontinuity. And what you might mean by this infinite discontinuity, we're talking about vertical asymptotes. This is actually called an improper integral. Okay, I'm going to give you an example. An example is just something like this. You have an integral from 1 to infinity of 1 over x squared dx. This is an improper integral. Okay, so you could have negative infinity to say 2, and then I can have, suppose I do have a function such as, let's say, 1 over x plus 2 dx. Okay, so this is also an improper integral. All right. So let me define another definition. Okay, so now what do we do, guys? We start by talking about the theory, and then we move to solving examples. Okay, so this is like the theoretical framework of this idea, and then we'll solve examples from there. Okay. Now, if I have an integral, say from a to t, f of x dx, if this exists for all values of t greater than or equal to a. Now, what does this mean? This condition tells me that this value of a here has to either be smaller than t or at least equal to t. Now, if this guy exists, okay, take note, guys, if this guy exists and this condition holds, all right, so then the integral from a to infinity f of x dx equals the limit as t goes large, integral from a to t f of x dx. Okay, so what does this mean, guys? This tells me that if I do have an improper integral, I can actually write it as an equivalence in terms of limits. Okay, so it means I can introduce a limit, a limit notion. Now I'll give you guys an easy example right now. So let's use the same example we have up top. So suppose I have 1 to infinity, 1 over x squared dx. I can rewrite this guy by introducing the limit notion. So this is going to be limit. Now this t is just a constant, guys. Okay, so if you like, you can use t, you can use k, you can use m, it depends. Okay, so I can just stick to t. T goes large, and I have from 1 to t f of x dx. Okay, so think about it this way. Let me show you guys something. Let's see, f of x dx, right? All right, so my f of x in this case, I need to fix this. I already know f of x. F of x is 1 over x squared, right? So I need to write this guy. Now, you have this guy. What does this mean? If you pass this limit as t goes large, that means this guy is going to infinity, right? Now, suppose you let it go to infinity. What does that mean? It means you have 1 to infinity f of x dx. So you see, guys, it's just a way to write an improper integral in terms of the limit notion. Okay, so we're writing an improper integral in terms of the limit notion. Okay, so another definition, guys. Now, if on the other hand, if this integral exists, for all values of t, but in this case now, my t has to be less than or equal to b. Okay, think about a definite integral. You have the lower bound and you have the upper bound. You know, that's a situation where the lower bound, the value on the lower bound is actually smaller than the value on the upper bound. Okay? Makes sense? So if this happens, then the integral from negative infinity to b, f of x dx. So guys, what do you guys think is going to be equal to in terms of the limit? Okay, so that means I have to write a limit, right? I'm going to replace this guy by a constant. Let's come here and just call it t. And of course, this guy is b, f of x dx. Now, I replace this portion, this lower bound, by a constant t. So that means t goes to, what is this value here? Originally, it had a negative infinity. Exactly. Okay, makes sense, guys. Now, we need these ideas, and that's why we're presenting it first. Okay, so now it's important to note, guys, in calculus 1, you actually learned about limits, okay? When do we say limit exists? Okay, so remember, the limit does exist in general when the limit from the left and the limit from the right coincides, right? When they are equal. Now, if we want to say that in another way, we'll say that when you compute the limit and it gives you a finite number, right? And that limit is finite. So let's say note the limit must be finite. Okay, so keep that in mind, guys. The limit must exist, and let me put finite in parentheses. The limit must exist, that is finite. Okay, you remember that from your knowledge of calculus 1. When you compute a limit, when it exists, what happens? It means it gives you a finite number. Okay. All right, let's move on. Let's proceed. Now, I need to tell you guys something we call now, these improper integrals have two types. We have the type 1, and then we have the type 2. Okay, so let's talk about the type 1. Now, if you have, let me write that guy in red, integral from a to infinity of f of x dx, and integral from negative infinity to b of f of x dx. These guys are actually improper integral of type 1. Are improper integrals of type 1. Okay, there are two types of this improper integral. We have the type 1 and the type 2. These sort of improper integral are type 1. Now, now we have to talk about convergence on divergence. Now, what does that mean? It means that when I compute that integral, will it give me, will it sum up to a particular number, a finite number? Will I have a finite number, or will I have some kind of finiteness or not? Okay, so now that brings the idea or the notion of convergence or divergence. So let me say the improper integral gross this guy. Of course, remember they are improper integral of type 1. This should be infinity right here. It should be infinity. These guys are actually convergent if their corresponding limit exists. Okay. I'm going to show you guys what that means in a second. All right, so and let me underline convergence and divergence if the limit does not exist. You guys remember DNE. If the limit does not okay, if the limit does not exist. Okay, so what does this mean, guys? I'm going to show you guys in a second. You have an integral a to infinity f of x dx. Now, I can actually, first step actually, when you have this kind of integrals, where one of the bound is infinity, one of the bound could be a positive infinity or negative infinity. Now, when you have this situation, you can, the first thing to do is to rewrite it. If I write this guy, I'm going from limits as t goes to infinity, right? A to t f of x dx. Now, when is this guy said to be convergent? Or when does this integral converge? This integral converge if this guy exists. So that means the existence of these limits determines the convergence of this integral. Okay, so now if the limit exists, now what does that mean? It means that the limit is finite. Okay, I hope that's a quick summary. That's a quick summary. And on the other hand, this guy, let's use a different color right now. So this guy, that's not a good color. Let's see, okay, let's do blue. Let's do blue. This guy is divergent. Okay, when what, guys? When this guy, when the least limits, when the limits DNE does not exist. So let me use an arrow to connect this guy. Okay. Keep that in mind, guys, because we need it. We need that idea. We need that understanding. Okay, so and if the limit does not exist, that means, of course, it gives you something like negative infinity or infinity. Okay, one more thing, guys, and then we're going to examples. Now, if both this guy and this guy, let's have a right here to infinity. If these guys exist, okay, now if they exist, guys, what does it mean? If this integral exists, that means that the integrals are convergent, okay, and that means that the limit exists, okay, and that also means that the limit is finite. Now you have to be able to connect the dots and see, equivalently what those definitions are talking about. So let me put in bracket, let me say are convergent. Okay. Then we can actually define this guy. Let me show you guys. Okay. So far, we've only seen like, a part where you could be going from negative infinity to a constant. And we also saw where you could be going from a constant on the bottom to positive infinity, right? So, but now we're seeing a situation where what happens if I go from negative infinity to infinity? Okay. This guy is the same thing. I can actually split it into two. And then this is going to be a to infinity f of x dx. And then also need to let you guys know that a is a constant, or a is a real number. A is any real number. Now, let me try to explain this with a number line, guys. Now, if I have this is just an intuitive understanding, okay? So if I have this guy, this is a line. Suppose this is the center, this is 0, right? The moment you have the center, you've splitted this guy into two parts. You got the negative part and the positive part, right? Now, suppose that over here, I have a negative 2. Suppose here I have a 2. Now, if my goal is to integrate from negative 2 to 2, I can actually do that directly if possible, right? But on the other hand, I can kind of have like a branching. I can go from negative 2 to 0, and then I go from 0 to 2. So that way means I'm doing negative 2 to 0, and then 0 to 2. So essentially, when this guy connect together, I'm just doing negative 2 to 2. Okay, so that's really what is going on. You're going from negative infinity to infinity, right? Suppose this is a number line. Let's call this guy 0. Or let's call this guy A. Let's not pick 0. Let's pick A. So we're actually saying this guy and then this guy. So that's why you see we have a negative infinity to A, and then from A to infinity. So just pretty much splitting it up into two parts. Okay. Now let's get started with our examples. Now in this first example, we want to evaluate an integral from a negative infinity to 0, 1 divided by 3x minus 5 dx. Now, the first thing you must be able to settle within you is what type of integral is this? This is an improper integral. And in this case, it's a type 1. Okay, we already said some second ago what the type 1 integral is. Now, solution. As a first step, this is a negative infinity. I have to rewrite this guy in terms of the limit notion. Okay. Limit as t goes to negative infinity. This is t to 0, 1 over 3x minus 5 dx. Now, I need to say, guys, that the improper integral are special types of integral. Okay, and for special type of integral, you treat them, for this special type of integral, you treat it specially in this manner. Okay, so now with this guy, that means that I have to first evaluate this guy and then take the limits. Okay. So this is limit as t goes to negative infinity. Now, how do you evaluate this integral? Now, this is the bottom, right? Take derivative of the bottom. What you have, guys? You have a 3, right? But what you have on top is a 1. I hope you guys remember the trick that we often do when that happens. Okay. When that happens, you just introduce a 3 over 3, right? So this is like, this is going to be 3 times 1. And then you have a 1/3 up front. Okay. Essentially, nothing changes, right? Because 3 divided by 3 gives you 1. So you're back to the problem you're actually answering. All right. Now, and why is that trick important? Because when you take the derivative of the bottom, you know, one of those techniques of integration is that when you differentiate the bottom and it gives you the top, you just write ln of the bottom. Okay. So we need that. So this is 1/3. And then we're good with ln of bottom. Okay, 3x minus 5. But remember, this is a definite integral. That means I have to go from t to 0. Okay. All right, so I still have my limit as t goes to negative infinity. It's a 1/3. Now we got to plug things in, right? We have to plug things in. All right, so this is going to be limits. Now, if you plug in the top, 3 times 0, you got a 0. 0 minus 5, you got a negative 5. Now, remember that when you do ln, you have to use the absolute value. Okay, if you don't use the absolute value, then it can actually mislead you. So minus, you got a ln of, this is going to be 3t minus 5. Now this is 1/3. You know how you treat limits, right? You can pull out 1/3. I got 1/3 right here. Limits as t goes to negative infinity. So I'm actually left with ln of absolute value of negative 5 is just 5, right? Minus ln of 3t minus 5. Amazing. So right now I need to pass my limits. If I pass my limit, guys, this becomes something like, now these guys are constants. But if over here, if you pass your limit here, t is negative infinity. So that means you have limit of this guy is just going to be, ln of this guy. Limit of the ln of this guy is going to be infinity, right? And that means you have infinity. What does that mean, guys? In this case, it's going to be a negative infinity. What does that mean, guys? Why is it going to be a negative infinity? You have a small number and you are subtracting from infinity. So that's going to be negative infinity. So what does this mean? It means it does what? It diverges. Okay. Let's do another example. Let's see if it does converge or diverge. In this example, we're going from, this is 4, this is infinity, e to the negative y over 2 dy. What's the first thing I need to do, guys? I need to rewrite in terms of the limit notion. So this is 4 infinity e to the negative y over 2 dy. This is going to be a limit as t goes large. T goes to infinity, right? 4 to t, e to the negative y over 2 dy. Now, in this case, now I have to first treat this guy. So this is limit as t goes to infinity. Now, if you integrate this exponential function, what do you get, guys? This is going to be a negative 2 e to the negative y over 2. But you have your bound 4 to t. Okay. So essentially what happens, negative 2 is a constant. You can pull it out. You got limit as t goes large. I'm going to be left with e to the negative y over 2, but I still got my bound 4 to t. Negative 2, you got limit as t goes large. Now you plug in the top and the bottom, so that way I have e to the negative t over 2 minus, if you plug in the bottom, you're plugging y equals 4. So you have negative 4 over 2. That means you just have e to the negative 2. Okay, so that's easy, guys, right? And negative 2. Okay, so right now I need to pass my limits. If you pass your limit here, guys, so what do? What is the limit? Let's use a red. What is the limit as t goes large of e to the negative t over 2? This is just going to be a 0, guys. Okay, do you guys remember how to compute limits? I mean, that's calc 1. In that case, you just have like 1 over infinity, and 1 over infinity is just 0. Okay, because exponential of a very large number is still the large number, infinity. It's still going to be very big. So that means I have a 0 minus e to the negative 2. Okay, e to the negative 2 is a constant, so you don't do anything with a constant. This is negative 2 times negative e to the negative 2. And talk to me, guys. This is just 2e to the negative 2, and that's it. So when we integrate this guy, now what do we say in this case, guys? Convergent or divergent? Is this a finite number? Yes. So then you say convergent. Okay. It's a finite number, then we're good. That means it does converge. Okay. Okay, so let's take another example. Now, if you have negative infinity to infinity, 1 divided by 1 plus x squared dx. Now, if you back up a little bit, guys, you remember that we had the situation where we said if you're going from negative infinity to infinity, you break it up into 2 bits. Okay, so I can actually do the same thing here and just, kind of break things up. So solution, negative infinity to infinity, 1 over 1 plus x squared dx. I want to break this guy up, negative infinity to 0. Think about this line. This is a 0, this is negative infinity, this is infinity. So I break this guy up here and break this guy up, okay? 1 over 1 plus x squared dx plus integral of 0 to infinity, 1 over 1 plus x squared dx. All right, so the integrand, guys, are actually the same, okay? So we have the same integrand. The only difference is the bounds. So that way I can make life easy for myself, right? Now, and each of these guys are improper integral of type 1. That means I can write them first in terms of the limit notion. T goes to negative infinity. You got t to 0, 1 over 1 plus x squared dx plus, what about this guy? T to infinity. This is going to be a t. This is 0, 1 over 1 plus x squared dx. Let me call this part, let me label this guy number 1. Let me label this guy number 2. All right. Now let's go on and deal with number 1. Okay. Let's deal with number 1, guys. But what do I know? To make life even more easy, guys, you can first, since they have the same integrand, the different thing is the bound. So when we have this situation, guys, what does this integral equal? This guy equals the arctan, right? Just arctan of x plus c. Okay, so let me pick number 1. Limit as t goes to negative infinity, t to 0, 1 over 1 plus x squared dx. I already know what this integral is, so I just have to care about the bound right now. Tan inverse of x from t to 0. Make sense? So that means I have the limit as t goes to negative infinity. Okay, so you have to plug in the top and the bottom. Tan inverse of 0 minus tan inverse of t. What is the arctan of 0, guys? The arctan of 0 is just 0, right? Okay, so that way, I'm left with limit as t goes to negative infinity of negative arctan t. Okay. Now, if you find these limits, this guy is just negative arctan negative infinity, right? And what does this give you guys? Do you remember? This guy gives us a negative pi over 2. Because if you sketch the curve of tan, there's an asymptote at pi over 2. Okay? You have the point of discontinuity over there. So this is pi over 2. That's 1. So we have to take care of the other guy, which we call 2. And that was 0 to infinity, 1 over 1 plus x squared dx. We actually write this guy as this, 0 to t, 1 over 1 plus x squared dx. So we know this integral already. We only need to care about the bounds. And that was a arctan of x, right? We're going from 0 to t right now. So this is going to be limit as t goes large. Now you plug in your top and your bottom. So you have a tan inverse of t minus tan inverse of 0. So this is kind of similar as before. The only difference is that the bounds are different. Okay, so this is 0. So this is arctan of infinity. Talk to me, guys. What is the arctan of infinity? That's just going to be pi over 2. Okay, so, but remember, major question we're trying to solve is this guy, which splitted into 2 parts. The first part gave us pi over 2. The second part gave us pi over 2. So what does that mean, guys? This integral is just pi. Absolutely amazing, guys. Now you see how powerful, this notion is with respect to the improper integral. Okay. Now, so far we've seen the case of improper integral of type 1. Usually we'll talk about, it's often called infinite intervals. Okay, infinite intervals. So we're going to move to a different perspective right now, which will lead us to improper integral of type 2. So let me say case 2. The first case are the infinite intervals, which we saw already. So let me come here and just do, okay. All right, so I can just write something around here. Just talk about infinite intervals, right? So case 2 now, we're actually going to discuss functions with discontinuities, okay? Function with a discontinuity. Okay, so we'll proceed. Now, let me give you an example, guys. If you have a function f of x equals 1 over x minus 2. Okay, let's remind ourselves. Over here, we have this guy. Okay. I bet that some of you are going to remember this, these stuffs. Okay, so this is just an asymptote. This point corresponds to 0 and -1/2. Got a 2 right here. Over here, we got a 4. Now, when x is 0, this is, we are plot over here. This is just a plot of this function. When x is 0, if you plug in 0 here, you have a -1/2. And that's why you have this guy. Okay. All right. So, what if we, in terms of integral, what if I'm told to integrate this guy? This is just going to be the area of a region which is infinite in a vertical direction. Now, it's amazing the beauty of, sketches most of the time, how it helps you to, visually understand what is going on. Okay. So then we can actually write this guy, x minus 2 dx. Now I'm going to explain the whole of this. Okay. See, this is 4. Now you might actually wonder and say, oh, but the integral doesn't have any kind of infinity on the bound. You're correct. But essentially, there is what we call the point of discontinuity. Okay. The point of discontinuity is that point at which there's an issue with the integrand. Now, in this integrand, let me put a red pen. In this integrand, now you're going from 2 to 4. What happens when x is 2, guys? When x is 2, you have a 1 divided by 2 minus 2, which is 1 over 0, which is infinity. Then there's a problem. Okay, so that means in the interval you picked, there is something that you need to avoid, or there is a point you need to avoid. And to avoid such points, that means that you have to introduce the limit notion. Okay, so that's what is actually leading us to the improper integral of type 2. In type 1, we had the infinite interval. That means on the bound, you have an infinity on the bound, whether negative infinity or positive infinity, or maybe in some cases, it can be from negative infinity to positive infinity on the same function, okay? But in the type 2, you necessarily don't have an infinity on the bound. It could even be a real number, okay? So, but there is a problem at one point within that interval you have on the bound. And this is a good example. So now let's make some definition. Now, if we have a function f, if this function is continuous on an interval a comma b, opened at one end, closed at the other end, and actually discontinuous at b, okay, then integral from a to b of f of x dx is going to be equal to, now what do we know, guys? This guy is continuous here, but discontinuous here. So that means I got to fix that point of discontinuity. So if I fix that point of discontinuity, that means that this is b, right? This is a to t. Okay, because you need to fix that point. Now, but in this case, put the sign right here from the left. Okay, provided the limit exists. because it's something to actually be able to rewrite. Is another thing for the limit to exist. Now take note, guys, a little, switch in notation. In this case now, when you have the discontinuity at B, that means your limit is as t goes to B from the left. All right, so you have B and then you have this little negative sign over there. Okay. Okay, so let's move on. Another definition. Okay, very similar to the first one, but not exactly the same. If f actually, okay, if f is continuous, okay, I missed the word is right here. If f is continuous on this time, you have open at this guy, but closed at this point. And discontinuous, it's discontinuous on the open end at A. And if you look at the first definition two, let's call this guy definition one, definition two. In definition one, it is open at the right end. Okay, and that right end is B. So that's the one that takes the little negative sign up front, which means from the left. Okay. And then it is in the second definition, it is open at the left end. All right. Then how do we write this? Integral from A to B of f of x dx is going to be the limit as t approaches A from the right. A to B f of x dx. Okay. Of course, provided if the limit exists. Okay, so you got to be mindful of the notation at this point, guys. In definition one, you're open at the right end. So that means you don't exactly hit the number B. So that means you can only talk about the left portion of that. Okay. So, and then in the second definition, you don't exactly hit A. That means A is not included, right? Do you remember when you have the open end, which means not included, and the closed bracket? When you have the bracket, it means it's included. All right. Okay, so let's move on, guys. Now that will lead us to safely, talk about the improper integral of type 2. Now, whether it converges or diverges, now that definitely depends on the limits. You remember that, guys, okay? So I'm just going to say convergent or divergent if the limits. Okay, so let me split it so that you guys don't get confused, okay? Okay, convergent if the limit exists. And then divergent if the limit does not exist. So you guys remember it's just DNE, does not exist. I'll give you guys a third definition and then we'll look at some examples. Definition 3. Now, what happens if f is discontinuous at a so-called point C, and that C lies between A and B? So take an example, guys. You have A here, you have B, and your C is lying here. And that's the point of discontinuity. Okay, so, and this guy, you have the integral of from a to c of f of x dx, and from c to b of f of x dx. If these integrals exist, then what happens? Then, now remember, when you're going from a to b, right? I can split it. Do you guys remember the splitting I mentioned earlier on? You can go from a to c, and then you can go from c to b. So then integral from a to b of f of x dx is actually, when you go from a to c of f of x dx, a to c, right? Plus when you go from c to b. Now, another way to think it, of course, this limits, this integral already exists, right? We already stated the condition here. Another fancy way to think about it is that this is c and this is c. It has to be opposite of themselves. So that place collapses. When it collapses, you have a to b on the left. That means on the right, you also have a to b. That means you're good. Okay. Now let's go do examples. In this example, suppose I have this integral Okay, so is this an improper integral? I mean, I need to know, right? I need to know if it's an improper integral. Yes, it is. Why? Now look at this bound. If you plug in 2, 2 minus 2, you got a 0 on the bottom. 1 over 0 is undefined. Then there's a problem. So solution, the limit as t goes to 2 from the right of this guy. Just want to show you guys, this guy's undefined, which implies that this actually means that the integral is improper. So you could even have a question like, oh, is this integral improper? You should also be able to check by the virtue of what we've done so far. So now I confirm that there's a problem at that point 2, okay? So remember, this is limit as t goes to 2 from the what, guys? Is it going to be left or right? It's going to be from the left. Now let me back up a little bit, guys. When the problem is on the lower bound, it's going to be like, a from the right when you do the limits. When the problem is on the upper bound, that means it's going to be the b in that case from the left. Okay. So this is going to be integral from t to 5, 1 over square root of x minus 2 dx. Okay, so that means I have to take care of this guy first. So, and then I bet that you guys can actually do that. So I'm just going to tell you what it is. X minus 2. This is t to 5. So now I got to plug in my bounds. So as t goes to 2 from the right, 2. If you plug in the top, you got square root of 5 minus 2. That's 3. Square root of 3 minus, if you plug in the lower bound, you got 2 of t minus 2. What do I know? Now, you want to compute this limit. You have t is going to 2, approaching 2 from the right. So this is just a constant. So that means I can just plug in 2 right here. Okay. So if I do that, this guy is going to be a 0. Perfect. So what does this mean, guys? Is this a finite number? Yes. So that means that this guy, this integral, does it converge or diverge, guys? What do you think? Is what? Convergent. Okay. Why is it convergent? Because this guy is finite. Okay, it's important to take note of that. Let's do another example. Integral from -1 to 1. In this case, we have a e to the x divided by e to the x minus 1, of course, dx. Think about it this way. Think about the line. You got -1 to 1. Okay, so this is a portion, this is 0. Now, whenever it's going from negative of the same number to positive of the same number, always think about splitting into 2. So that means I have to go this route. This is e to the x over e to the x minus 1. -1 to 0. E to the x divided by e to the x minus 1 dx plus 0 to 1 e to the x divided by e to the x minus 1 dx. That's just me splitting it into 2, guys. Okay. Now we need to see what situation do we have here. We have the same improper integral situation, right? And in this case, the problem is going to be at 0. How do I know? E to the power of 0 is 1. 1 minus 1 gives me 0. So you have e, you have 1 over 0 that's undefined. So there's a problem here. All right. So, but the integrand are the same. The bounds are different. So why don't I just work smart? Check this guy. What's it going to be first? In this case now, remember, if I differentiate the bottom, it gives me the top. So that becomes ln of the bottom. Okay. So just like before, similar to what we did before, let's call this guy 1. Let's call this guy 2. So let's talk about 1. -1 to 0, e to the x divided by e to the x minus 1 dx. Okay. So remember, the problem is at 0, right? That means that this guy is going to be the limit as t. Remember, when it's about the upper bound, that means this guy is 0 from the left. -1 to t, e to the x divided by e to the x minus 1 dx. Okay. So we already computed the integral. So we just write ln of this guy and you plug in your bound. So this is going to be limit as t goes to 0 from the left. You plug in the top and you plug in the bottom. Okay. So this is ln of e to the t minus 1 minus ln of, right here, right now you have e to the -1 minus 1. What do you guys think? Now I need to compute this limit, okay? I need to compute this limit. This guy, now when as t goes to 0 from the left, what happens, guys? This is just going to be undefined. Okay, so how do I know, guys? How do I know? If you plug in t equals 0, remember from the left, e to the 0 is what? 1. 1 minus 1 is 0. What is ln of 0? Infinity. Okay, but you're approaching it from the left, so that means this guy is going to be a negative infinity. Now let me show you a trick, guys. Now this part is already, now what happens when, okay, what happens when you have this guy diverges, right? So that means number 1 is divergent. Now, this is the thing, guys. This number 1 here is divergent. Don't bother about this guy. The moment this part is divergent, then everything diverges. Okay? So don't waste your time trying to do number 2. Number 1 is already divergent. Just you make your conclusion. So let me write, don't do other side. Why? Since 1 is divergent. Okay, you guys know what I call 1, right? I mean divergent, not different. Yes. So what's going to be my conclusion, guys? So integral from -1 to 1, e to the x divided by e to the x minus 1 dx is just going to be what? Is divergent. So just is. Make sense, guys? Okay. All right. So if that makes sense, okay, let's kind of see one more example. Okay, so you have from 0 to 1 dx divided by square root of 1 minus x squared. Okay, is this an improper integral? Absolutely yes, guys. This is an improper integral. Why? Because if you plug in 1, you have 1 minus 1 on the bottom. You have 0. Square root of 0 is 0. So that means you have a situation with 1 over 0, which is undefined. So that means I have to, under each, the situation is on the top, right? So that means limit as t goes to 1 from the left, 0 to t, dx divided by square root of 1 minus x squared. Well, I hope you guys remember from 7.3 that when you have integral of 1 over square root of 1 minus x squared dx, this is just the same thing as inverse sine. Okay, so these are things you guys need to remember actually, so that you don't have to go through the long procedures again. Okay, so that means this guy is just going to be equal to limit as t goes to -1, 1 from the left, So this is going to be sine arc sine x. What about the bound 0 to t? So that means apparently I have a limit as t goes to 1 from the left, arc sine of t minus arc sine of 0. Well, what is arc sine of 0? It's just 0. Now t goes from 1 to 1, the left of 1. So that means this is 1. Right? So that means I'm going to do arc sine of 1. Okay, so an arc sine of 1 is what, guys? Pi over 2. So what do we say, guys? It does what? Converges. So that means it is convergent. Does this make sense, guys? Okay. If it does make sense, that's it on 7.8. So I'll see you